Section 4.3, we're examining how the first derivative and the second derivative affect the shape of a graph. So we take the graph of a function f. We already know that the first derivative tells us about the slope of the tangent line. So the first derivative can therefore tell us information about where the function f is increasing and where the function f is decreasing as well. In addition to telling us where the graph of the function f would have a horizontal tangent line, and also where we might find a corner or a cusp where the first derivative would not exist. Okay? Features such as that. Now, if we want to establish information about a local maximum or a local minimum, we can also use the first derivative in what is called the first derivative test. So anytime that we have a critical number, recall that a critical number is a value c such that the first derivative is equal to 0 or the first derivative does not exist. After finding that we have a list of critical numbers, we can then use the first derivative function itself to test in intervals, subintervals of the domain that is, surrounding the critical numbers in order to determine the increasing and decreasing nature of the function f around those critical values. So if the function f is differentiable on some open interval, and within that open interval we have a critical number, either the slope of the tangent line will be 0 there or the derivative would not exist there, we can test to the left and the right of that critical number in order to determine the nature of the function. Now if the function f had a removable or an infinite discontinuity or a jump discontinuity, okay, if it was not continuous, that is, then we wouldn't use the first derivative test anyway. First off, in order to determine whether we have a possible local maximum or local minimum, we first need the point itself to exist at the maximum or minimum. So let's say we had a point that was a potential local maximum, as we've shown here as one possible example. Well, it could be then that that f prime of c is equal to 0 at that point, of course. That would be if the derivative exists. That's Fermat's theorem. Or it could be that the point itself exists and we have continuity, but maybe the derivative does not exist there. Like if we had a corner, for example. Okay, that could be the case. In other case, if we have the point whereby the c is a critical number, we can then take values to the left and the right of that critical number, being careful not to travel so far from the critical number that we would have gone past another critical number. So we really want to know where all the critical numbers would be throughout the entire domain before doing this. Okay, so we want to test to the left and the right of our critical number, and if we find that the first derivative is positive to the left of our critical number, but negative to the right of our critical number, well then analytically that means that the function would have to be increasing and then decreasing around that point. And since it must be continuous, we'll put those pieces together and say, well, that means there must be a local maximum there. Okay. So we're using the first derivative here, though, in order to try to tell us analytical information about the function from which it was derived. And that information isn't going to include y values. If we wanted to know y values, we would have to have at least an initial point to start from, and we can use that along with the derivative information in order to sketch the curve, or better yet, to have an actual symbolic function, like a full-on f of x is equal to something, okay, which in some cases we would have. Okay, in any case, that's how we can use the first derivative to determine if we have a local maximum by the use of the first derivative test. Suppose that c is a critical number of a continuous function f. Then, if f prime changes from positive to negative, that would be from increasing to decreasing, then you must have a maximum at c, a local maximum. Well, if f prime changes from negative to positive in subintervals around c, then you must have a local minimum. Okay? But it's also possible that if you have either the derivative is equal to 0 or the derivative doesn't exist, in either case, but you still have continuity, you still have a critical number, it could be that the derivative to the left and the derivative to the right are both of the same sign. For example, if we have increasing to the left and increasing to the right of our critical number on a continuous function, then we would not have a maximum or a minimum. Okay? And we would know that as well. Okay, if we had decreasing and then decreasing on either side, we could also have information telling us we have no maximum or no minimum as well. Okay, so these are some shapes of some curves that we could find locally around those critical numbers by use of the first derivative test. Okay. Now we can also use the second derivative to tell us analytical information about the shape of a curve. Okay? How does the second derivative apply? Well, the second derivative tells us the rate of change of the first derivative, or the rate of change of the rate of change. So if the first derivative tells us the slope of the tangent line, the second derivative tells us how fast that slope is changing and how it is changing. So for example, if the second derivative were a positive quantity, if the second derivative is positive, that would be telling us that the first derivative is increasing. Okay? That the first derivative is increasing. So if we had a function whereby we had the slope of the tangent line, here we go, right? If the slope of the tangent line were already, let's say, for example, let's say I already have that the slope of the tangent line is positive. Let me say the slope of the tangent line is equal to 1. But then it increases maybe to where then the slope of the tangent line becomes 2. And then it increases further to where the slope of the tangent line becomes 3, and so on and so forth. Okay, so if we were to plot the smooth continuous curve through these points whereby the slope continues to increase, the shape of that curve would be like this. When the slope of the tangent line increases as we look to the right, we call that shape of the curve concave up. Okay, it's called concavity. Concavity is the numerical measure of the rate of change of the slope of a function. But in fact, this feature called concave up would also exist when the slope is negative, and this is how it would look. If we continue this shape around, we're going to call this like a bowl shaped up, and I think of it in this way. If a shape of a curve on an open interval is concave up, then it would be a shape that would hold water. That's if it were raining on this, the water would collect in this basin right here. So this is entirely concave up. But even if there was only a portion of this, even if we had only a portion of the curve that was sort of bowl shaped, even though this wouldn't collect water and it would roll off, if this curvature would continue in this fashion, we would create an upwards facing bowl shaped region. So this would be concave up right here. Okay. So this still satisfies the definition over here of concave up. The second derivative would be positive over here. The second derivative is positive. And so we can see that even with negative slopes, right? If we have, let's say the slope of this tangent line right here maybe is m is equal to -5 or something like that. We move a little further out along the curve. Notice that we are still decreasing. That is, f prime is still negative, but now the slope is not as negative. It's not as steep. Right? And as we approach maybe a point right here, again, it's still a negative slope, but not as negative. So maybe m is equal to -1. Okay. Now notice along the whole region from, it's open at the left, but until this point right here, okay, until about here, right, within this whole region right here, the first derivative, let's call it f prime, is less than 0. Okay. But because these slopes, the value of f prime is increasing, right? We have f prime is -5, then -3, then -1. Okay, then within this entire region, it would also be true that f double prime is greater than 0. Right? So we have the first derivative is negative, but the second derivative is positive along this portion of this curve. Now when we go to the other half, the second half, from this point outward, okay, along this part of the curve, we have that f prime is going to be positive. The first derivative of it is going to be positive, right? That's considering where this is in black. This is the graph of y equals f of x, right? So the first derivative is positive over here, but the first derivative is also increasing over here. So on this side over here, the second derivative would also be positive. So the second derivative is positive along this entire curve. So we can see how the first derivative and the second derivative combined can give us information about the shape of the curve. Okay, this region right here is what it looks like if both the first and second derivative are positive. But this piece right here is like what it would look like if the first derivative is negative while the second derivative is positive. What about this point right here? That point in blue, okay, what would be the nature of the derivatives there? Well, the first derivative at that point is going to equal 0 at that point in blue. In other words, the x-coordinate of that point would be a critical number of the function f. And what about the second derivative? The second derivative is still going to be greater than 0 there. Okay, the second derivative at that point is greater than 0. Okay, because it is still concave up. That is still at a point where the slopes are increasing. Right? The rate of change is still increasing continuously as we move through that point. Okay. All right, on to concave down. Concave down would be curvature such that water would roll off. So an entire feature that looks like that, a bowl shaped downward like this, that would be concave down. Okay, I'll set this one over here. Okay, so that would be like concave down right there. If it were raining on top of this, it would just wash off the sides. Okay, the left portion of this, right, this would be considered to be concave down. This right here, on this shape right here. All right, let's take a look at the slopes of some tangent lines here, right? We have a positive slope here. We have also a positive slope here, but not as positive, right? So let's say this first one is where m is equal to 3, right? Positive 3. But then along this tangent line, maybe we have m is equal to 2. And then maybe along this tangent line here, maybe we have where m is equal to 1. So notice that the first derivative is decreasing. It is positive throughout, right? Right, so we have f prime is positive throughout this entire region, okay, but the first derivative is decreasing because we see the slopes of the tangent lines decreasing. So the second derivative would be less than 0 then. Okay, so we have this is the shape along a part of the curve, an interval of the curve, an open interval, where the first derivative is positive but the second derivative is negative. Okay, and then we have this shape right here, right? The right half of this curve over here. Let's take a look at some tangent lines. Let's take a point like right here. The first derivative at this point right here would be negative. Okay, so let's say m is equal to maybe negative 1. Okay, so we have the first derivative there is negative. Okay, and then if we move out further along to the right, okay, then we get the slope of the tangent line is more negative, right? It is decreasing at a faster rate. So let's say m is equal to negative 2. And move out even further, right? It gets even more steep. So here we have m is equal to negative 3. So we have the first derivative is decreasing again. That is the rate of change of the first derivative, right, is negative. Right? The rate of change of the first derivative is negative along this branch. So the second derivative is less than 0. Anywhere where the second derivative is less than 0, right, then the shape of the curve along that region is concave down. Okay, so let's say this is a graph of y equals f of x right here. Okay, this is concave down. All right, now there at a point, if on a continuous function, a point where concavity changes, if we have a change from concave up to concave down, or from concave down to concave up, the point where that change happens is called an inflection point. And since the inflection point is related to concavity, we can determine the locations of inflection points by using the second derivative. An inflection point is where there is a change in concavity. It requires continuity, that is, the point itself needs to exist on the curve. This shape right here is concave down, right? Concave down, but then if we had a portion that was concave up, notice right at this point there's a change that happens. Right, here we go, purple on that one. All right, this point right here would be an inflection point. Consider the concavity to the left and to the right. Okay, so on this region right here, right, this is bowl shapes downwards. So on this region we would have f double prime is less than 0. Okay, on this interval, subinterval of the domain. Okay, where the curve I'm sketching is the curve of y equals f of x. So we can tell from the shape of the curve itself when the second derivative is negative. And we can see from the shape over here, okay, that the second derivative would be positive along this portion of the curve. So we have a change in concavity, concave down to concave up. Right? We have concave down changing to concave up. And that change happens at a point that exists because this function is continuous there, and so we call that point an inflection point. Okay, now it's possible to have the change happen where it is concave, okay, where the concavity changes in another direction, and furthermore, where I want to emphasize here, okay, whereas it may look like at this inflection point, it may look like we have a horizontal tangent there, and maybe I should even consider that that's a possibility. Like maybe we have a horizontal tangent line here. It could be that f prime is equal to 0 right there. But the first derivative doesn't necessarily have to equal 0 when the second derivative would equal 0, which it could right here. If the second derivative changes continuously from negative to positive, we would expect it to go through a value of 0. The second derivative is 0, but really we just need it to be continuous there. Okay, we need the function to be continuous there. So in fact, the second derivative doesn't even really need to exist at the inflection point. It's the function, the curve itself has to exist at the inflection point. So a possibility of one way we can locate where an inflection point occurs is we might want to consider, well, do we have any points where the second derivative is equal to 0? Okay, and then we can test around that, just like we did with critical numbers in the first derivative. Okay. Another thing to look out for is where is the second derivative not existing? Because anywhere where the second derivative does not exist, we then want to check to see, well, does the function exist there? Because as long as we still have a continuous function, okay, a continuous function, even if the second derivative doesn't exist, there's still the possibility of an inflection point. Okay, an inflection point is going to be where there's a change in concavity. We'll take a close look at this graph right here, okay, so we can see the different types of the different types of inflection, some different types of inflection points we might find. Okay, all right, but I want to take a look at this graph over here. It has a couple different features than this graph. First, we have that on this portion right here, up until about maybe right there, okay? So I'll say maybe about right here, and that point exists on the curve itself, okay? That's going to be an inflection point. So this is the graph of y equals f of x. Now on the interval up to the inflection point itself, up to this line right here, okay, this curve shows that it is concave up. That is right. We have a very steep decreasing. Right? It almost looks like it's going vertical there, right? Okay, so it is a decreasing function, but it is decreasing less and less. Right? If you can see the slope of the function is more extreme. If you were riding this on a roller coaster, it's a pretty steep roller coaster, but you are going down at a faster rate along this portion as opposed to this portion. Right? You're at least slowing down a little bit as you're moving down that hill. Okay? So that is that the derivative is increasing. The first derivative is increasing. In other words, the second derivative would be positive on this portion right here. Okay, so it is concave up, okay, on this portion of the curve. And then on the other side of this point right here, the curvature changes. This is now concave down. That is now the second derivative is going to be less than 0. The slopes of the tangent lines are getting more and more negative. On this case, it started negative and getting more and more negative. Okay, so it is concave down. What is important, it doesn't matter that the first derivative is negative when you're determining concavity. And it's possible to have that the first derivative is positive, but the second derivative is negative. You can have those combinations as well, as we've already looked at, above here. So since we have a change in concavity at this point, and that point is included on the graph, that is, it is continuous there, then that point is called an inflection point. Now, Another feature, though, that is different about this curve and the way I've sketched it versus this curve over here. Over here, I said, well, I tried to sketch it so that the slope of the tangent line at the inflection point was also equal to 0. So we had, well, f prime was equal to 0 there. And I might add, also that at this point, nice and smooth and continuous here, f double prime would also equal 0 at that particular point right there, the way I have sketched this. Okay. But compare that to over here. If we were to sketch a tangent line to the curve right here at the inflection point itself, notice that the slope of that tangent line is not 0. Right? There is no requirement for an inflection point. There's no requirement that the first derivative would have been 0 there at all. In this case, we have the first derivative is negative at that point. But notice at that point, since this is nice and smooth and smoothly transitioning from a positive second derivative to a negative second derivative, if that happens smoothly and continuously, then f double prime must have passed through 0. All right? So f double prime would equal 0 at that point. Okay. Again, that does not mean that f double prime has to equal 0 at an inflection point. It could be that f double prime does not exist at an inflection point. Take a look at this curve here, and let's find a point on this curve. There is at least one point on this curve where we have an inflection point, but the second derivative would not exist at that point. Now notice along this entire curve, it is continuous, right? All these points are included. Okay? But along this portion right here, it is nice and smooth. All right? Let's mark in purple here where we find some inflection points. We have that this is concave down, right? This is concave down throughout this region from A to B, but then it becomes concave up from B to C. And the change on a continuous curve in concavity would occur at an inflection point. So there is an inflection point right here. Right? Now we have from C to D, it is concave down. Okay, so we have a change at a continuous point on the curve, a change in concavity from concave up to concave down, so C would be an inflection point as well. Now what happens at D? D is included on the curve. It is still continuous there. And we have the concavity was concave down to the left, but concave up to the right. Okay? However, we notice that the point itself was a corner. Okay? We have a corner at D. And if there's a corner on a function, and this is the graph, okay, this would be the graph of the original function y equals f of x, by the way, that we're looking at here. Okay. If there's a corner on the graph, okay, then notice that, right, the input is lowercase d, then that means that f prime of d does not exist. If the second derivative doesn't exist there, if the first derivative doesn't exist at d, then we can't take the second derivative there as well. So f double prime of d as well does not exist. So even though the second derivative does not exist at that point, when we look to the left and the right of it, just like we did with critical numbers, right? It's just critical numbers are the name we give to these values in the first derivative. Okay, so it's kind of like a critical number of the second derivative, which in a sense is, because a critical number, if you will, when we're dealing with the second derivative, would be a critical number with respect to the first derivative, because the second derivative is the derivative of the first derivative. In any case, it's another type of a critical number. I just want to be careful when I say that, because we really only, when we say critical number, we are specifically referring to values in the first derivative that would equal 0 or not exist. Okay? And I'm just saying that we can take the first derivative of a first derivative and still call this a critical number of a first derivative when we're talking about the second derivative. Okay, no, that's confusing, but it's a kind of a critical number, right? All right, so the second derivative does not exist at this point, but to the left and the right of it, we have different concavities. Okay, the concavity has changed, so that point is therefore an inflection point. What makes it an inflection point? if the concavity changes to the left and the right, and if the function actually exists at that point. It must be continuous there. Okay, so I'll box this. Okay, so notice we have, in that graph, we also have a corner at where the input is E. So E, f of E. So that is that f prime of E, where E is the input here, right? Not the natural growth constant E, but the input variable value is E. The constant f prime of E, that does not exist. And since that does not exist, then f double prime of E also does not exist. Okay. But this is not an inflection point. Why would this not be an inflection point? Because there is no change in concavity. It is concave up to the left and to the right of that point. No change in concavity, then it's not an inflection point. But at this point right here, point P, we do have a change in concavity. It changes from concave up to concave down. And so we do have an inflection point here at P. Okay, so it is possible to have an inflection point. Okay, I'll draw more attention to this. It is possible to have an inflection point where the second derivative does not exist. Okay, but it's also possible for the second derivative to not exist, yet you don't have an inflection point. In any case, we have a way for checking for concavity now. How do we check for concavity? Okay. We can find what we can say are the critical numbers with respect to looking at the second derivative. If you find all the values such that the second derivative is equal to 0 or the second derivative does not exist, you can then test to the left and the right of those values in subintervals of the domain. We are also required to have the function must be continuous at those points. The same requirement existed when we were dealing with finding maxima and minima, local maxima and minima, by use of the first derivative. Okay, so I hope you can see that the testing that we did, the first derivative test, okay, that's where we had to find the critical numbers, derivative is 0 or derivative does not exist, and then test to the left and right of them and see if it changed, positive to negative, negative to positive, or if it stayed positive, positive, negative, negative, in order to determine maxima and minima. That test is the same test that we can apply to the second derivative, which would tell us about concavity and inflection points. If the second derivative has its quote-unquote critical numbers to check around, if you find that the second derivative goes from positive to negative, right, goes from positive to negative, that would be from concave up to concave down. And from concave up to concave down means you found an inflection point, right? Not a local maximum, because you're talking about the second derivative. It would be inflection. If the second derivative went from negative to positive, right? If the first derivative went negative to positive, we got a local minimum. If the second derivative goes from negative to positive, we have concave down turning to concave up. That means change in concavity. That means inflection point. When the first derivative went positive to positive around a critical number and on a continuous point, right, we had no max, no min. Similarly, if the second derivative at what is a critical number for the second derivative, in this case where the second derivative wouldn't have existed, right? But if we have concave up to concave up, then we have no inflection point. Okay, and the same would be true if we had negative to negative. Negative to negative means we don't have the feature. What about it? Is it sufficient to say that when the derivative is equal to 0, that guarantees we have one of these features? If f prime of c is equal to 0, does that mean that f must have, okay, then does f have a guaranteed local max or min? In other words, if we find out that the first derivative is equal to 0, right, is that going to tell us that for sure there must be a max or min there? And the answer to that is no. It's not sufficient just to say the derivative is equal to 0 and therefore the feature's there. Here's an example, right? At this point right here, okay, we have the derivative is equal to 0. We have f prime of c is equal to 0, but we do not have a max or a min. It's not enough to look just at the point. That's what I'm suggesting now, okay? To just look at the point itself is not enough. We have to look within a neighborhood around that point. That is, look to the left and look to the right to see the true nature of that point, like whether it has the characteristic or not. And over here, there's another situation where f prime is equal to 0, but we do not have a max or a min. So it is not a guarantee. Just because the derivative is equal to 0, it doesn't guarantee we have the feature. Similar story then for second derivative. Okay, if f double prime of c is equal to 0, okay, then does that guarantee that f of c, okay, is an inflection point? Is it a guarantee? And the answer to that is also no. It does not guarantee, okay, that it is an inflection point. Before we jump ahead to this thing called second derivative test, okay, let me show you an example of a function whereby the second derivative is equal to 0 at a point, okay, but you do not have an inflection point. Okay? Okay, so let's choose a function whereby that would be the case. Let's consider the function y, or call it f of x, right? F of x is equal to x to the fourth. Okay? So we know the graph of y equals x to the fourth. Remember that from algebra class, from pre-calculus class. Y equals x to the fourth. Between like -1 and 1. Okay, it goes through 0, 0, right? It goes to 1, 1, -1, 1. Right, in between those, it's kind of like this. It kind of tries to stay close to the x-axis. Okay, but then outside of those bounds, 1 and -1, it becomes very, very steep, and it rises very quickly. Here's the graph. Okay, let's take a look at the first derivative first. F prime of x is 4x cubed. And now the second derivative, f double prime of x is 12x squared. Let's find the values where f double prime would equal 0. Okay, so if we said 0 equal to 12x squared, notice that that would have a solution of x is equal to 0. So that means that a point c f of c on this curve would be the point where c is equal to 0, and f of 0 would be 0 to the fourth, which is also equal to 0. Okay. That would be this point right here. Just looking at the curve, okay, even though we have that the second derivative is equal to 0 there, right? We have f double prime of 0 is equal to 0. This is not an inflection point. Can we tell what the concavity is? What's the concavity to the left? What's the concavity to the right? Okay, if you take a look at the shape of this curve. This curve is concave up throughout its entire domain. Now, how can you test to see what the concavity is? By choosing test values. Test values around the critical numbers. Now, x is equal to 0 is a critical number of the second derivative, if you will. Right? We really only call the numbers in the first derivative that make it 0 or not exist. We call those critical numbers. Right? But I'll call this a critical number of the second derivative, let's say. Okay, we can test around them. Okay, let's choose some test values. Let's imagine that we have, this is the whole domain. Okay, so the domain is, for this function, the domain is -infinity to positive infinity for y equals x to the fourth. Okay, so this is where c is equal to 0. So we have an interval to the left, we have an interval to the right to consider. Okay, here are our intervals. This is the interval from -infinity to 0. It's an open interval because we already know what happens at 0 in the second derivative. The second derivative would be 0. And then we have the interval to the right. That's from 0 to infinity. And I want to test on either side. Okay, either side of those of this number right here in the second derivative. So I'm going to say, what is f double prime of x? So I want to choose a value within each one of these intervals. Okay, so say for instance I choose, and it doesn't matter what number we choose, anywhere within this interval we can choose a number. Let's take -1. So f double prime of -1. I mentioned earlier, you want to make sure you're not choosing a value that goes beyond another critical number. Well, we already found all the critical numbers for this. That is, we found all the values where the second derivative is equal to 0. There was only one of them in this example. So that's it. So we only have these two subintervals. Let's say I plug in -1 into the second derivative. Well, the second derivative is this. So we're going to get 12 times -1 squared, and that's just equal to 12, and 12 is a positive number. So we have that the second derivative is positive, right? So we have the second derivative is positive along this interval, and that means that the shape of the curve is concave up along this interval. Now we can go and test on this interval. And we should already know what the answer is going to be because we have the picture right here. We can see that it's concave up on this side as well. All right, so there's no change in concavity. Let's choose a value in this subinterval, right? Like we can choose +1 or any other number. I'll choose 5. What's f double prime of 5? Well, all I really need to know is whether it's positive or negative. So I get 12 times 5 squared. That's 12 times 25. That is clearly going to be a positive number, so that is greater than 0. So we have f double prime is greater than 0 over here, so we still have concave up. So we have the curve is concave up to the left, concave up to the right, even though the second derivative was equal to 0 there. Right? So is this an inflection point? It is not an inflection point. So this curve has no inflection point. Okay, so thus far for this section, which has a lot of material in it, we have what's called the first derivative test, a way to check for where a function is increasing or decreasing on its domain. Find the critical numbers, break up the domain into subintervals surrounding those critical numbers with respect to the first derivative now, right? And then use the output of the first derivative on those subintervals to determine if the function is increasing or decreasing on those subintervals. And then we have the test for concavity. After defining concavity, to test for concavity, you find the values of the second derivative that are equal to 0 or the second derivative does not exist. So think of the critical numbers with respect to the second derivative. Okay. Test to the left and the right within the subintervals of the domain around those quantities and determine from the output of the second derivative in the subintervals whether the function is concave up or concave down. Further, labeling the points where there's a change in concavity as inflection points. Okay. We can similarly label points with reference to critical numbers. We can label those in general as critical points. Critical points can be local maxima, local minima, or these points right here, which are saddle points, which also I would mention, by the way, one of these points right here, okay, where the first derivative is equal to 0, it would also turn out the second derivative is equal to 0 at a point like that. This leads us to the next test of this section, which is called the second derivative test. The second derivative test is another way to look for local maxima and local minima. So the result of the second derivative test is the same as the result of the first derivative test. They are both built to target if there's a local maximum or a local minimum at a point. What the difference with the second derivative test to the first is that the second derivative test uses concavity to find a conclusive result if it can. Look at this point right here at the local maximum. This point at the local maximum was found at a critical point where the first derivative was equal to 0. Now, in order to use the second derivative to assess whether this is a maximum or a minimum, it requires that the second derivative can be assessed at that point. That is, the second derivative must exist in order to do the second derivative test. So let's suppose that both derivatives exist. If both of the derivatives exist at this point right here, then it must be the first derivative is equal to 0. That's Fermat's theorem. And notice the second derivative would be negative. This is concave down here. So I'm going to add that note in right here on our graph. F double prime of C is less than 0 there. Now that we know what the second derivative tells us. Okay, so if the first derivative is equal to 0, which we have if we have f prime of c is equal to 0, that is, it must exist because we need the second derivative to exist as well if we're doing the second derivative test. An advantage of that second derivative test is this. In either the first derivative or second derivative test, in either way, you have to establish what the first derivative is. So that's the same for both tests. Where the difference is in the first derivative test, you have to then check values in the subintervals to the left and the right of the critical number. That is, in the first derivative test, you have to evaluate the first derivative for two different values, an input to the left and an input to the right, in order to reach a conclusion. The second derivative test only requires us to test at the point itself, which is one input into the second derivative. So this would be more convenient if finding a second derivative was relatively easy to do, if it wasn't too expensive to just calculate the second derivative. Like if it was a polynomial, okay, the second derivative is pretty easy to find. Okay, and then if plugging the critical number in, okay, gives us a conclusive result, right, then that's convenient. But if the second derivative is hard to find, or if the case is that the first derivative or second derivative didn't exist, then we wouldn't be able to use the second derivative to do this test. We would have to use the first derivative test in that case. Yeah, but we should be introduced to the idea that the second derivative, concavity, can be used as a way to check if there is a local maximum or a local minimum. This is a case where we have a local minimum. There's a local minimum there. If we could apply the second derivative test, then we would have to have a second derivative existing there. So let's say the first derivative exists. F prime of c would have to equal 0, therefore, at this point. But what would the second derivative at c have to be at this point? Because of the shape of the curve, the second derivative would be positive. If the first derivative is 0 at a point, but the second derivative at that point is positive, you must have had a local minimum at that point. Now over here, what we have is if the first derivative is equal to 0 at c, okay, and the second derivative also turns out to equal 0, you might have an inflection point. Remember that in order to determine if it's truly an inflection point, we have to check the concavity to the left and the right of that point. That's actually what we need to do. Is it possible for the first derivative to equal 0 and the second derivative to equal 0, but not have an inflection point? Yes. Go back to here. F of x equals x to the fourth. Notice f prime of 0 is equal to 0. And f double prime of 0 is also equal to 0. But the point itself was not an inflection point. Yeah? So it is possible for both of the derivatives to be equal to 0 at a point and not have an inflection point at all. If the first derivative is equal to 0, and then if you find that the second derivative is also equal to 0, we have no conclusion, right? It is inconclusive. Well, the second derivative test would be inconclusive. The first derivative test then would be conclusive because we can test to the left and right and find out if it's increasing and increasing, then we know for sure it's not a maximum or a minimum. It's possible for the first and second derivative to both equal 0, as would be the case here as well. It's possible for both of them to equal 0 at the same point and to end up with no max or no min. It's also possible for both the first and second derivative to equal 0 at the same point, okay, and to have a local min. Okay, if the first derivative is 0 but the second derivative is less than 0, local maximum. First derivative is 0, second derivative is greater than 0, local minimum. That is the second derivative test. Okay, we must have f double prime exists, right? F double prime of c, well, it must exist in order to use the second derivative test. Okay, the second derivative has to exist in order to use the test. Otherwise, if you can't use the test and you still want to know if you have a max or min, you revert to the first derivative test. And you just go straight back to that anyway. Okay? If f double prime of c is equal to 0, though, then the result is inconclusive. All right? And the way to unlock the test, to even consider the test, is that we must have f prime of c is equal to 0. Okay? So what is required? F prime of c is equal to 0. So critical numbers, but critical numbers where the tangent line would be horizontal. If you had f prime of c does not exist, well then automatically we would know that f double prime of c is also not going to exist. So we wouldn't be able to use the second derivative test. If f prime of c doesn't exist, you could still have a max or a min, and there you would have to use the first derivative test. Okay? If it's inconclusive, then what do? We must use the first derivative test in order to reach a conclusion. Okay? If either f double prime of c is equal to 0 or f double prime of c does not exist. Okay, so now we can find out where functions are increasing and decreasing with the increasing and decreasing test. We can also establish from that information about where there might be local maxima and local minima with the first derivative test, or the second derivative test can tell us where we have local maxima and local minima. The first derivative test ultimately is going to be more robust of a test. It's going to tell us more information because the second derivative test sometimes will just fail and we'll have to revert to the first derivative test. The other thing we have in this section, of course, is concavity itself. We can test for intervals of concave up and concave down the same as we can test for increasing and decreasing, but we're just doing it with the second derivative instead of the first. And we can check for inflection points. Those are points on the curve whereby the concavity changes from either up to down or down to up. Now, for this section, I want to use notation for these critical numbers, since we have critical numbers in the first derivative and critical numbers in the second derivative. Okay. Let's just use this notation for this lecture, okay, or for now. Let's let C1, I'm going to let C1 represent critical numbers, the traditional critical numbers, okay, the critical numbers of f. That is that f prime of C1 is equal to 0 or f prime of C1 does not exist. Right? That makes these values critical numbers of the original function f. All right, so f would have points where the tangent line's horizontal, right? Or you can't find the derivative, but it's still a point on the curve. And let's let C2 for this section, we'll let C2 represent what will be the critical numbers of f prime. Okay? That would be where the derivative of the first derivative, that is f double prime then, the derivative of a derivative, right? So f double prime is equal to 0 or f double prime does not exist. Okay, so these are the critical numbers of f prime. That means we are using the second derivative. Okay. All right, and let's try some exercises here. So consider first the function, the polynomial function, f of x equals x to the fourth times the quantity x minus 1 cubed. A, find the critical numbers. By critical numbers, I mean the C1 values. That's where either f prime of C1 is equal to 0 or f prime of C1 does not exist. Now, this is a polynomial function here. All right, this function's polynomial, so its domain is all real numbers, and it is smooth over its entire domain. The derivative is going to exist throughout the entire domain. So the critical numbers for this example, okay, are all going to be values of x such that the first derivative is equal to 0. Okay? And we'll take a look at we could take a look at some more examples whereby possibly the first derivative doesn't even exist at some points. Let's start with this polynomial. After you find the critical numbers, then part B, what does the second derivative test tell us about the behavior of the function at our critical numbers? Okay. Again, the C1s, those would be the critical numbers coming from the first derivative. Okay, so we're not actually being asked to test for concavity by itself, okay, or find intervals of concavity. We're asked ultimately to find information about local maxima and local minima. The second derivative test, okay, is about testing for local max or local min, or it's going to be inconclusive. Part C, what does the first derivative test tell us about the behavior of f at those C1s? And the first derivative test also is designed to tell us about local maxima and local minima. Okay, so for this first question, I'm not asking anything about intervals of concavity, at least not yet. Okay, maybe we'll add that on later. Let's start by finding the critical numbers. Part A, well, we need the derivative, f prime of x. Okay, we'll take that by the product rule because I don't feel like expanding this polynomial. So we have 4x cubed times x minus 1 quantity cubed plus x to the fourth times 3 times x minus 1 quantity squared. What do we want to do? We want to set this equal to 0. So 0 equals this, and then we can solve it. Well, in order to solve that equation, I'm going to want to factor this. So let me find some common factors. We have an x cubed here, and we have x to the fourth here. Okay, so I'm going to take out an x cubed, and then we also have x minus 1 cubed here, but an x minus 1 squared over here. So I'm going to take out x minus 1 squared. I'll open up a bracket. So we are left with, let's see, we're going to be left with a 4, a factor of 4 here, and another factor of x minus 1 here as well. Plus, over here we have another factor, x. Oh, and we also have a 3, and I like to put the 3 in front. So I'm going to call this a 3x. Okay? All right, so that should be correct, right? If we distribute this back to here, we would get 4x cubed, x minus 1 quantity to the third power, right? And then this would be 3 times x to the fourth and x minus 1 squared. Very good. Let's simplify this further so we can set each of our factors equal to 0. So we have x cubed, x minus 1 squared. This is what? 4x plus 3x is equal to 7x, and then minus 4. Now we can find our critical numbers by solving this. We have x is equal to 0. We have x is equal to 1. And we have x is equal to 4/7. Okay, those are the values of C1 then. Okay, this set of values right here. All right, in general, we would also want to check to see where the derivative does not exist. Okay, so I'll just make a note here for your notes that f prime of x exists on all real numbers, right, from negative infinity to positive infinity. Okay. All right. Now, part B said to find out what does the second derivative test tell us. Okay. It tells us, well, if we have f prime of c is equal to 0, okay, then we want to check f double prime of c. If f double prime of c is positive, then that means the shape of the curve there would be concave up, and therefore we would have a local minimum. If f double prime of c is negative, then that means we have concave down, and therefore we would have a local maximum. And if double prime of c is equal to 0, we have a big question mark. It is inconclusive if f double prime is equal to 0. That's the second derivative test. So we have f double prime of x that we need to evaluate now. That is the first derivative of f prime. So the derivative of that, x cubed times x minus 1 squared times 7x minus 4. So if we were to take the derivative of this product of three functions, we would have to apply the product rule twice. And we could do that. Another thing we could do is we could go back to this combination right here where we have a product of two functions plus a product of two more functions, And so up here, if I take the derivative here, we can take the product rule of this and the product rule for this, okay, and add those two together. So it's either we're taking the product rule and the product rule of these two combinations, or we're taking the product rule within a product rule of this combination. And either one, it's up to you. So take the derivative of 4x cubed at the start, that's 12x squared, and then that's times x minus 1 quantity cubed, plus, we've got 4x cubed times the derivative of x minus 1 cubed. Okay, so that's 3 times quantity x minus 1 squared. Now the product rule in the second product here, the derivative of 3x to the fourth is going to be 12x cubed. And then that's times x minus 1 quantity squared plus 3x to the fourth. Okay, and then we have the derivative of x minus 1 quantity squared is 2 times x. All right, 2 times x minus 1, and that would be to the first. Okay. All right, so we have two product rules. All right, product rule times 2. All right, and what do we want to do here? To the second derivative test, we want to evaluate the second derivative at 0, at 1, and 4/7. So we want to plug in 0, we want to plug in 1, we want to plug in 4/7. Okay, so we can simplify this from here, try to factor it out and clean it up, or we can go and plug in those quantities. So let's find out what is f double prime of 0 equal to. Okay, then we'll find f double prime of 1 and then f double prime of 4/7. Okay, f double prime of 0. Well, this group is just going to equal 0 if we plug in 0 because we have a factor of x right there. Okay, this group right here, we plug in 0, that's also going to equal 0. This group here, also going to equal 0. So we got that x right there. And this group also. Right? That's going to equal 0. So that's not that bad. So f double prime of 0 is equal to 0. What does the second derivative test tell us? If the second derivative at a critical number is equal to 0, inconclusive. Okay? Inconclusive where the critical number is equal to 0. Okay? C1 is equal to 0. That is what the second derivative tells us. Not a whole lot. It basically tells us, go look at the first derivative. That's what it says. And then f double prime of 1. F double prime of 1. Okay, so let's go green, huh? So this group right here, okay, has a factor of x minus 1. So therefore, this is going to equal 0. Because I have 1 times this. Okay. Plus, this group here also has a factor of x minus 1. So this one's going to equal 0. This group here, factor of x minus 1. This group here, factor of x minus 1. Okay. So each of those are going to equal 0. So f double prime of 1 equals 0. So the second derivative test is inconclusive when C1 is equal to 1. Now, if we wanted to know what the location of the critical points are on the curve, we can plug the critical numbers 0, 1, and 4/7 back into the original function f. If we find out what is f of 0, we would have the y coordinate, which in this case would be 0. So the point 0, 0 is a critical point. If we plug in 1, notice we're going to get 0 also. So the point 1, 0, that would also be a critical point. If we plug in 4/7, well, we're going to take 4/7 to the power of 4, okay, times the quantity 4/7 minus 1 cubed. When you find out what that is as a fraction, that would be the y coordinate for the critical point where the input is 4/7, right? So we can use this information to then find y values from the original function, just as we can use these quantities to find information about the slope, increasing, decreasing, by plugging them into the first derivative. And we can find out information about the concavity by plugging these values into the second derivative. All right, so these quantities tell us different pieces of information about the curve, okay, about the function analytically, geometrically, depending on whether we plug these values into f of x, into f prime of x, or into f double prime of x. Okay, so let's see what we can find out about f double prime of 4/7. So I think to plug in 4/7, since we're going to get a bunch of quantities here that are going to be, let's see, this one's going to end up being negative, right? This one's going to be positive. This one's going to be positive. I see that because this is going to be 4/7 minus 1 is negative, and then we're cubing it, so that's negative. But here, 4/7 minus 1 is negative, but then we're squaring it, so we're getting positive. So see, we're going to get a combination of negatives and positives here. And I'm ultimately interested in, is f double prime of 4/7 going to be, in the end, positive or negative? Okay, so I want to clean this up then a little bit. Okay, I want to see if we can simplify f double prime. Alright, so I'm going to clean up this expression a bit. We have 12x squared times x minus 1 cubed. This is going to be 12x cubed times x minus 1 squared. 12x cubed times x minus 1 squared again, so those can combine. And then this will be a 6x to the 4th times x minus 1. Okay. So 12x squared times x minus 1 cubed. We're going to have plus 24. Okay, so we have 12 here and 12 here. 24x cubed times x minus 1 squared. Plus 6x to the 4th. Times x minus 1. Okay, we can factor out a 6x squared times x minus 1. Alright, that would leave us with, 2 times x minus 1 squared, plus 4x times x minus 1 plus x squared. Okay, now let's evaluate f double prime at 4/7. 6 times, 4/7 quantity squared. 4/7 minus 1 is negative 3/7. All right, so this product here we know is going to be a negative quantity. All right, so that's helpful. All of this is going to give us something negative. That's all I want to know about this, is if it's positive or negative. And then this, I want to find out if this is going to be positive or negative. Well, we're going to have 2 times, negative 3/7 squared. This is going to give us a positive quantity. Plus, this is, 4 times 4/7 times negative 3/7. Well, that's going to give us a negative quantity. And then plus 4/7 squared, and that's a positive. Let's find out overall, is this going to be positive or negative? Common denominator, right? They all have a denominator of 7 squared. It looks like they all have a denominator of 7 squared, and they are all going to have a common factor of 2. So I'm going to take out 2 over 7 squared. 2 over 7 squared, and this would be left with this would just be a 9, right? Negative 3 squared is 9. Took out the 2 and the 7s. Okay, so I'm going to be left with a 2 times 4, which is 8, times negative 3. All right, so negative 24 from that. And then this one, took out the denominator, 7 squared, took out a 2. This is 4 times 4 is 16. I took out a 2, so this is leaving me with an 8. Good, now I can figure out the sign of this factor. Right, 2/7 is, of course, going to be a positive, so we have a negative times a positive, and then 9 and 18 is 17, minus 24 is negative. So a negative times negative is going to output positive. Alright, so we have f double prime of 4/7 is greater than 0, so that means that the function is concave up through the point, the critical point, where c is equal to 4/7. Okay, from the shape of the curve, that means that this function, therefore, by the second derivative test, okay, f has a local minimum, okay, at the point where c, or c1, I called it, is equal to 4/7. Okay. Right, now part C, All right, part C was, what does the first derivative test tell us about the behavior of f, okay, at the critical numbers? Okay. All right, so the first derivative was this, right, 4x cubed, x minus 1 cubed. I'm going to take this one. I'll take this one right here. Okay, x cubed times x minus 1 squared times 7x minus 4. I'll go to a new layer. All right, so f prime of x. This is part C. All right, we're doing the first derivative test, that is testing for local maxima and local minima through use of the increasing and decreasing nature of the function around the critical values. So we have C1, the set of C1s, 0, 1, and 4/7. Okay. So we're not checking at those values, we're checking around those values. Let's show that geometrically here. If I graph the number line, this represents all real numbers in the domain. I can mark off on here where we have the different critical numbers. 0, put it above, 0, this can be 1, and then a little more than halfway between those two we have 4/7. All right, we're not testing at those values. We know what's going to happen. If we plug in any of those three values into the first derivative, we're going to get 0. Okay, so we're going to plug in values surrounding those, okay, within subintervals. Okay, the intervals then for us to check, we would have negative infinity to 0, and then we're going to have the open interval from 0 to 4/7. Okay, and then we have the open interval from 4/7 to 1, and finally we have the interval from 1 to infinity. Okay, and we are going to be testing the first derivative, so f prime of x, right? We're not plugging in the critical numbers, we're going to be plugging values in within those intervals themselves. All right, so let's take f prime of, let's say, -1. Okay, what is f prime of -1 going to be? So we can use, all right, the function right here. F prime of -1 is what? -1 cubed times, it's going to be -2 squared times, let's see, -7 minus 4 is -11. Okay, we just need to know if this is positive or negative. That's all we're after here. So we have a negative number, right? -1 cubed is negative. Negative squared is positive, and then this is negative. A negative, positive, negative outputs a positive. So f prime of -1 is greater than 0. Okay, therefore the function is going to be increasing on this interval. So we have f is increasing from negative infinity to 0. Okay, let's test in this interval. Let's take f prime of 1/2. Okay, that's less than 4/7, but greater than 0. F prime of 1/2 is then going to be, let's see, we had x cubed, so 1/2 cubed, that's a positive. 1/2 minus 1 is -1/2, but then we're squaring that. And then we have 7 times 1/2, which is 7/2 minus 4. Okay, so 1/2 cubed, that's going to be positive. -1/2 squared, that's positive. 7/2 minus 4, 4 is 8/2, so this is going to be negative. So this is overall negative quantity. So f prime of 1/2 is less than 0, so the function f is therefore decreasing on the interval from 0 to 4/7. Let's check in this interval between 4/7 and 1 then. Okay. Let's check. All right. Okay. So let's try 5/7. All right. So f prime of 5/7. Okay. So first we have x cubed. So we have a positive number cubed. That's just going to be positive. And then we have a quantity that's going to be squared, and so that's guaranteed to be positive as well, right? This one's going to be a -2/7. And then we got 7x minus 4. Well, 7 times 5/7 is 5, so we have 5 minus 4, and that's just 1, so that's positive. So overall, we have that f prime of 5/7 is going to be a positive number, so the function is increasing on the interval 4/7 to 1. And then from 1 to infinity, let's test, how about, let's test 2. So f prime of 2, we have 2 cubed, that's positive. And then we have 2 minus 1 squared, so that's 1 squared, that's positive. And then 7 times 2 is 14, 14 minus 4, and that's positive. All right, so we get positive, 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 and that's overall going to be positive there. So this is increasing on 1 to infinity as well. All right, so we have the function is on all real numbers, right? It's defined on all real numbers. It's increasing from negative infinity to 0, and then the derivative is equal to 0 at 0, so it's flat right there, and then the function is decreasing until we get to 4/7, and then the derivative is equal to 0 there, so it's flat again. Okay? And then, right, only for an instant, right, instantaneously has a horizontal tangent line, and then it is increasing, and then the derivative is equal to 0 again, and then it increases again. Okay, this doesn't tell us about the y values by looking at the derivative, but it does tell us about the shape of the curve. So the overall shape of the curve is one that it increases, and then it smoothly and continuously decreases, and then it goes through a min, and then it increases, and then it flattens out, and then it continues to increase again. All right, so that's an exaggeration maybe, but that's the overall shape of this curve over all real numbers then. Okay, and what is the first derivative test tells us? Well, the first derivative test is really about telling us the locations of local maxima and local minima. We have here, right, it looks like local max, and we have here what looks like a local min. Okay, these are both local ones, not absolute ones. All right, so by the first derivative test, we see that the function has a local maximum at c1 is equal to 0, and okay, it also tells us that we have a local minimum, okay, when c1 is equal to 4/7, right? That's, you know, we established that earlier, and I would say it took a little more work maybe with the second derivative here, but we found that it had a local minimum at 4/7 earlier as well. And the first derivative test concludes that we have neither a max nor a min at c1 is equal to 1. So that's what the first derivative test tells us. Okay, let's go on to another step, step D. Okay, since we've done all this work, state the intervals where f is increasing and the intervals where f is decreasing. Okay. So using the first derivative here, we see the function is increasing from negative infinity to 0, also from 4/7 to 1 on that open interval, also on the open interval from 1 to infinity. Okay. F is increasing, okay, on those three intervals, right? Negative infinity to 0, right? 4/7 to 1, and 1 to infinity. It's not increasing at 1 though. All right, it's not increasing at 1. At 1 is actually where the derivative is equal to 0. Okay, so we know this because for any value of x within any of these subintervals, f prime is then going to be greater than 0. Okay, and we have that f is decreasing on the interval between 0, right, and 4/7. So we also have that information. All right, what about concavity? We can add that in here as well. State intervals, okay, where f is either concave up and the concave down. Okay, so we need our second derivative then. Now, in order to find that, we would need to set the second derivative equal to 0. We also want to know in general where the second derivative does not exist. This is polynomial though, so the second derivative is going to exist everywhere. So we could take the second derivative and set it equal to 0. I think this would be the easiest form of the second derivative to set equal to 0. Okay, so let's work with this here. So 6x squared, x minus 1, and then we have this whole quantity out here. Okay, so let's find a way to clean this up so we can set this equal to 0. Okay, so let's see. One way, let's see, I can factor out x minus 1 from these first two groups. That would leave us with what? 2 times x minus 1 from the first group plus 4x in the second group. And then there's a trailing plus x squared out here as well. Right. Okay, so then let's see, what would this be? So we'd have x minus 1 times, we have 2x and 4x is 6x, and then minus 2, and then plus x squared. Okay, so 6x squared, x minus 1. Now I'm going to expand this. So 6x squared, we get what? Minus 2x minus 6x is minus 8x, and then plus 2. Plus x squared, so 6x squared times x minus 1, this is going to be what, 7x squared minus 8x plus 2. Alright, kind of a nasty quadratic there. Okay, so here's our f double prime of x. Now f double prime of x exists for all real numbers. Okay, so we don't have to check for where it doesn't exist. Okay, exists for all real numbers. Okay, no need to check where it doesn't exist, but we do need to check where f double prime of x is equal to 0. Okay, so we said 0 equal to 6x squared times x minus 1 times 7x squared minus 8x plus 2. And then we're going to test in intervals around those values. Alright, so first we have x is equal to 0, and then we have x is equal to 1. I'm going to call these the C2 values, by the way. C2 and C1 seem to be overlapping for these two. But then we need to set this equal to 0 as well. Let's go to the quadratic formula. Okay, in fact, let's start with the discriminant. Start with the discriminant on this. B squared minus 4ac, okay, in this case is what, 64 minus 4 times 7 times 2. So what's 8 times 7 is 56. 64 minus 56 is 8. Okay, so the discriminant is greater than 0, so this is going to have real solutions. So we get x is equal to negative b, which is 8, plus or minus the square root of the discriminant, which was 8, over 2 times 7 is 14. Okay, so this is what? This is going to be 4/7. Convenient, right? Plus or minus 2 root 2 over 14, which is root 2 over 7. Okay, so we have x is equal to 4 plus or minus root 2 over 7 then. Okay, so if we break up the number line over these quantities, we have what? We have x equals equal to 0, we have 1. Right, root 2 is about 1.4. So 4 and 1.4 is about 5.4, which is less than 7. So this 4 plus root 2 over 7 is less than 1. 4 minus root 2, okay, would be about 4 minus the square root of 2 is about 2.6. So 2.6 over 7 is also less than 1. So we have 4 minus root 2 over 7, and we have 4 plus root 2 over 7. we can figure out numbers to choose that are within these subintervals. Right? Like you could approximate this with your calculator if you want to, and then you can choose a value that is less than this but more than that. For instance, so the square root of 2 is about 1.4. So 4 minus root 2 is about 2.6. 2.6 over 7. Well, then I can choose 2/7 or 1/7 even, right? As a test value. A potential test value would be something like 1/7, and that would be fine. Okay, something between these two numbers would certainly be right in the middle. 4/7. That would be between the two. 4 plus root 2 is about 5.4 over 7. Well, certainly 6/7 is more than that. Okay, so I'm going to mark the locations of our C2 values here in red. Okay, and then we can choose test values. Less than 0, I'm going to choose -1. More than 1, I'll go ahead and choose 2. Okay, so we have 1, 2, 3, 4, 5 test values to choose. Where are we testing them? We're looking for intervals of concavity. To check concavity, we would go to the second derivative. Here's our second derivative right here. So recall we checked already what the second derivative is at 4/7. So f double prime of 4/7 we found earlier was positive. So we already know that it's concave up. It's concave up on this region right here. Okay, so we have to test still. Okay, we have to test in this interval, this interval, this interval, and this interval. We have 4 intervals remaining to test on. Okay. Those intervals are from -infinity to 0, from 0 to 4 minus root 2 over 7, from 4 plus root 2 over 7 to 1, right, and then 1 to infinity. Okay. All right, and on each one of those intervals, we're going to be finding out what is f double prime of x. Okay, so for instance, we're going to find out what does f double prime of -1 look like. Okay, positive or negative. We just need to know positive or negative on the interval, right? F double prime of 1/7, f double prime of 6/7, and then f double prime of 2. Okay, so how we can organize our testing. Here's one way. Because we already have this written as a product of factors, I can use a tabular method. It's create a table where the head of each column is one of those factors. So we had 6x squared was a factor, x minus 1 was a factor, and then 7x squared minus 8x plus 2 was a factor. And the product of these factors, okay, would be f double prime of x. And we're going to plug in test values of x. The test values of x we've already selected, right, are -1, 1/7, 6/7, and a positive 1. And we're only checking to see if f double prime is going to be positive or negative in each of these cases. Okay, so for instance, take -1 as your x value, plug it into 6x squared. Well, you're squaring a real number, so you're getting positive. In fact, no matter what real number you choose, when you square it, you're going to get positive. And since 6 is always positive, that's not going to change it. So these are all going to be positive right down the line. Oh, wait a second. This shouldn't be a 1, right? This should be 2 as the test value, because I don't want to get 0 there, right? We're doing f double prime of 2. Okay, so you plug x equals 2 into this. Okay, x equals -1 into x minus 1, you get a negative number, right? 1/7 minus 1, negative. 6/7 minus 1, that's also negative. But 2 minus 1, that would be positive. How about 7x squared minus 8x plus 2? And here's what I'm going to do here. This is a quadratic, and a quadratic has a shape of a parabola. The leading coefficient is positive, so we know that it's shaped up like this. We also know what the intercepts are. Okay, that would be the x-intercepts. Those are found by using the quadratic formula, and we have those here. So we have 4 plus or minus root 2 over 7. Okay, so this right here, for instance, is 4 minus root 2 over 7, but this one is 4 plus root 2 over 7. Okay, so we can evaluate just this factor right here to see if it's positive or negative by using the sketch of the graph of this parabola. Okay, 4 minus root 2 over 7 and 4 plus root 2 over 7, of course, are both positive numbers. So if we plug in a number like -1 into this, plug in a number like -1, we would be on a positive part of this graph. Okay, we would be above the x-axis. Right? We're analyzing this quadratic right here. Okay, 1/7, okay, is right here. We've marked right here, right? We have 4 minus root 2 over 7, 4 plus root 2 over 7. 1/7 is to the left of 4 minus root 2 over 7, but 6/7 is to the right of 4 plus root 2 over 7. So 1/7 would put us at a point somewhere over here. That's going to output positive. 6/7 would put us somewhere over here. That's going to output a positive. And 2 is also going to be somewhere out here. So that's going to output a positive as well. So for x is equal to -1, f double prime is going to be positive times positive, which outputs negative. For 1/7, we get f double prime, right? So f double prime of -1 is less than 0. F double prime of 1/7 is positive, negative, positive. That is going to be negative. F double prime of 6/7 is positive, negative, positive. That's also negative. And then for f double prime of 2, and we get positive, positive, positive. That's going to output positive. All right. We have that this function is going to be concave down from -infinity to 0. It's also going to be concave down from 0 to 4 minus root 2 over 7. It's then actually going to be concave up. All right, it's going to be concave up between 4 minus root 2 over 7 and 4 plus root 2 over 7. Then it's going to go back to concave down again. Okay, and then it's going to go to concave up. All right, so we have concave up right here. So if we wanted to locate where inflection points would occur, we have a continuous function here for all real numbers. We have concave down to concave down, no inflection point here. But then we have concave down to concave up. So we're going to have this point right here, the point with this coordinate right here, that's going to be the location of an inflection point. Okay, because we have changing from concave down to concave up. Then we have behavior changing from concave up to concave down at this value, so that's also going to be an inflection point right there. And then we have concave down changing to concave up at 1, so this is going to be an inflection point as well. Okay, so we have f is concave up on the interval from 4 minus root 2 over 7 to 4 plus root 2 over 7, and on the interval from 1 to infinity. And f is concave down then on these 3 intervals right here. Okay. So f is concave down, okay, on -infinity to 0, also from 0 to 4 minus root 2 over 7, okay, and also from 4 plus root 2 over 7 to 1. And with this example, I would think that you should have everything you need to do even the most complicated looking polynomial type examples you might run into. Whether the exercises you try are as difficult as this or less challenging than this, right? You should be able to see a lot of the nuances that you can apply with the calculus and with the algebra as well. Okay? So let's take a look at an example now that's not polynomial, and with some slightly different questions being asked here in a different way. Given the function g of x equals 5x to the 2/3 minus 2x to the 5/3, A, find the intervals of increase and decrease. That would require the first derivative. Okay, we're going to be testing the first derivative around the critical values. B, find the local max and local min values. That can be done by either the use of the first derivative test or the second derivative test. Since we're already finding intervals of increase and decrease, that is, we're going to be testing within the subintervals anyway with the first derivative, I would suggest we might want to just use the first derivative test after following up to part A. C, Find intervals of concavity and inflection points. Well, concavity requires that we do a test with the second derivative. We have to find the critical values of this for the second derivative of this with the second derivative, and we have to test in subintervals around those critical values to find out where we are concave up and concave down. And then wherever we have a point that is on the curve where the concavity changes, that point would be labeled an inflection point. In order to find the local max and min values, those would be y values. That means we're going to want to find ultimately the y values so we can plot them as points. And in order to find the inflection points, that means we also are going to need y values, right? Remember, a maximum is a y value. A minimum is a y value. All right, a point is the combination of both the input and the output, so we need both coordinates, x and y. Well, with those points and knowing the behavior and the shape of the curve, we can come up with a reasonable sketch of the graph for this function. So let's start off with part A. We need to find the first derivative, and this is the function g. So we need g prime of x. Power rule, so we have 5 times 2/3 times x to the negative 1/3, and then minus 2 times 5/3, and then we have x to 5/3 minus 1 is going to be 2/3. I want to clean that up a bit. Okay, intervals of increase and decrease, we're going to need to have those critical numbers. So this is 10/3, but this is also 10/3, so I'm going to factor out 10/3 from both of these. This leaves us with x to the negative 1/3, which is the same as 1 over the cube root of x, or 1 over x to the 1/3. And then minus x to the 2/3, well, that's the cube root of x squared. So that's one way in which we can write this. Okay. All right, I'm curious about the domain of this function overall. We want to know what the overall domain is, so then we can subdivide the domain into subintervals around the critical numbers. And the domain for this function is, since we're dealing with cube roots here, and we have nothing in the denominator to be concerned with, then the domain is from negative infinity to positive infinity. And I didn't ask for the domain, but we really overall do need the domain so that we know, where we're working with this function. Okay. We'd also want to consider the domain of g prime, because that's going to indicate to us where the derivative does not exist. Okay, g prime of x does not exist where? At x is equal to 0. In other words, the domain of g prime is x is not equal to 0. Or in interval notation, of course, negative infinity to 0, open, union, 0 to infinity. So we now have the domain of g prime as well, which is helpful for finding a critical number. Okay, we have x equals 0 as a critical number. Now, what about where does g prime of x equal to 0? Okay. 0 is equal to g prime of x is equal to 10/3 times, we got the 1 over the cube root of x, minus the cube root of x squared. Okay, well, ultimately set this equal to 0, right? So where is the cube root of x squared equal to 1 over the cube root of x? Right? Well, we can cube both sides of the equation, and that gives us x squared is equal to 1 over x, multiply by x, which is x is not equal to 0, right? And we already checked that in the domain. We get x cubed is equal to 1. Okay. Now, x cubed is equal to 1 has more than one solution if you deal with complex numbers, but we're only dealing with real solutions. Okay. All right, recall x cubed minus 1 equals 0. If we set it up that way, we can factor x cubed minus 1 as x minus 1 times x squared plus x plus 1 set equal to 0. But x squared plus x plus 1, okay, the discriminant for that would be negative. B squared minus 4ac is going to be 1 squared minus 4 times 1 times 1. That equals negative 3, which is less than 0. Okay, so this part right here has no real solutions. And the only solutions then to this equation, the only real solutions are x is equal to 1. Okay, so we have x equals 1. Okay, is the only real solution. Okay. So reminder from pre-calculus, right? How to do that. But also, here you go. How about graphically, by the way? How do you know this is only one solution? What if you were to graph the function y equals x cubed minus 1? Graph y equals x cubed minus 1, so use a graphical approach. Well, the graph of y equals x cubed, first of all, looks like this, and then minus 1 is a vertical shift downward. So if we have a graph that looks like this. And if we wanted to know when does 0 equal x cubed minus 1, we look at the graph where the y value is 0. That would be this point right here. Okay, solutions to this equation can be found by looking at this point right here, and there's only one of these points, hence there is only one real solution to the equation. In general, the degree of the polynomial tells us how many solutions there are. That's from the fundamental theorem of algebra. For this equation, 2 of the solutions are complex, only one of them is real. All right, we just found the critical numbers then, right? The critical numbers, we have x equals 0 because that's where the derivative did not exist, and x equals 1 because that's where the derivative is equal to 0. So the critical numbers, right, C1, that set includes 0 and 1. Now, part A is about testing for increasing and decreasing. Okay, so let's set this up. We have, I'll sketch my real number line. This is all real numbers here from the domain. Okay, the domain was all real numbers, negative infinity to positive infinity. That's the domain of the original function, right? The domain of G. And then we have, so we have 0, we have 1. Okay. Okay, at each of those places, so at 0, the derivative doesn't exist. Okay, that's where G prime does not exist. And at 1, that's where G prime is specifically equal to 0. Just making a note of that. We want to test within these intervals right here. Okay. The intervals we're testing in are from negative infinity to 0, open, and then from 0 to 1, that open interval, and then from 1 to infinity. And we're going to be testing in G prime, right? The first derivative. We're testing for increasing and decreasing. So let's choose some values here. Okay, choose some values to test around. Okay, so this is critical, this is critical. Okay, so let's take negative 1. I can take that. I can take 1/2 or any number between 0 and 1, and anything greater than 1. So I'll take 2. Okay, so G prime of negative 1, okay, figure out what that is. Okay, G prime of 1/2, let's figure out what that is. And finally, G prime of 2, let's figure out what that is. Okay. So here's G prime of x right here. Okay, we have G prime of x equals 10/3, right, times 1 over the cube root of x minus the cube root of x squared. We could choose to, well, we could just plug the numbers in and evaluate it from here, okay, or we can try to simplify this. Let's see what happens if we try to simplify this. Common denominator would be cube root of x. So you multiply the cube root of x squared times the cube root of x, you get the cube root of x cubed, which is just equal to x. So you can write this as 1 over the cube root of x minus x over the cube root of x, or 1 minus x over the cube root of x. That'll make our evaluation a little bit easier then on each of these. Starting with negative 1 then. G prime of negative 1, okay, we got the 10/3 is not going to change the sign of this output. We just want to know if it's positive or negative, okay? 1 minus x, well, if x is negative 1, then we're going to get a positive up here. 1 minus negative 1 is positive, but the denominator, the cube root of that negative x, that's negative. So this overall is going to give us a negative value. G prime of negative 1 is less than 0, therefore. What about 1/2? We got G prime of 1/2, which is equal to 10/3, okay, then we get 1 minus 1/2, well, that's positive. And the cube root of a positive number is going to be positive, so this is overall positive. So G prime of 1/2 is greater than 0. And finally, G prime of 2. Okay, so we have G prime of 2 is equal to 10/3 times, we have 1 minus 2, that's negative, and the cube root of a positive is positive, so this is overall going to be negative. So g prime of 2 is less than 0. What does this tell us in terms of increasing and decreasing? If the first derivative is negative, right, then the function is going to be decreasing. The first derivative is positive, the function is increasing. And then we're back to negative first derivative again. Okay, so it's going to be decreasing again. Okay, what about we're talking about local max and local min, because we can already see what's going to happen there. We have g prime is equal to 0 at 1, so we know that the function is flat right here, a horizontal tangent line, right? So therefore there is a local maximum when x is equal to 1. Okay. We also have right here, we had the derivative did not exist here, right? We couldn't evaluate what the derivative was here, but the point itself existed on the function. It was continuous here. Okay, so g prime did not exist, right? But g of 0 does exist. The function is continuous there. What was g of 0? We can evaluate real quickly. 5 times 0 minus 2 times 0, so that's just 0. So it exists. So I'm going to put it here as just a point, right? Whereas I put this little horizontal dash to show that it's in fact a, horizontal tangent line. So we do in fact have a local min right here, actually. Okay, we have a local min at this point right here. We have a local max at this point right here. All right, let's start stating this information. Part A was asking for intervals of increasing and decreasing. All right. So let's start with increasing. G is increasing on the interval from 0 to 1. That is an open interval. Okay? And G is decreasing, okay, on the intervals from negative infinity to 0 and 1 to infinity. So negative infinity to 0 and 1 to infinity. That would be fine. And that's fine. We got increasing, we got decreasing. All right, just as a reminder, find the local max and local min values. So that's actually asking for the y values at the min and at the max. Okay, so let's state where there is a min and where there is a max, and then let's state what those values are. Okay, so we have a min at 0. Okay, we have a local min, okay, at the point where g at g of 0, and g of 0 is equal to 0. So the actual value of the min is 0. That's the y coordinate. That's the value of the local min. The local min is equal to 0. The point on the curve is the point 0, 0. We have a local max at g of 1. Okay. Okay, local max at g of 1. And what is g of 1? It's going to be 5 minus 2, right? So that's equal to 3. So at g of 1, all right, which is equal to 5 times 1 to the 2/3 minus, minus 2 times 1 to the 5/3, that equals 5 minus 2 is equal to 3. So the value of the local max, there we go, the value of the local max is equal to 3. Okay, and the location of that max is at the coordinates 1, 3. So we have a point at 0, 0 of interest and a point at 1, 3 of interest as well. That'll help us in creating our sketch. Okay, so our graph so far we know has a point here at 0, 0. Okay, and this is the graph for y is equal to g of x. Okay, we know that g prime of 0 itself does not exist. So this is not smooth at this point. Something else happens there as we look around it. And then we go out to the point 1, 3. And here we have a local max, and we know that it is smooth around here. The derivative does equal 0. If it's a local max here, then we know within a little neighborhood here, Okay, it's going to be nice and smooth like that. Okay, so we also have, right, what else do we have? We have that it continues to decrease out to the right. Now, we don't know quite how yet. I mean, does it decrease down like that, or does it approach an asymptote like that? This would also be decreasing for all time as well. Okay, how would we know the difference? Well, if it was doing something like this, notice it would be concave down over this entire interval. But if it were to approach an asymptote, it would have to go through inflection. It would have to go from concave down through inflection to concave up if it might be approaching an asymptote. So let's take a look at concavity to figure that out. Okay, but we do know that it is decreasing, okay, at least on this side and throughout this entire interval. It is going to be decreasing in some fashion. All right, it is also decreasing over here, and it is increasing in here. Okay, so we're starting to piece this together. So for part C, we're going to look for the intervals of concavity and the inflection points. Then C. Let's take a look at G double prime of x. Okay, so we have the derivative of 10/3 times x to the negative 1/3, right, minus, let's see, x to the positive 2/3. Right, that looks good. And then we can apply the general power rule. We're also going to do the constant rule. Take out the 10/3. Okay, so we get 10/3 times negative 1/3 x to the negative 4/3 minus 2/3 x to the negative 1/3. There's our second derivative right there. Okay, so let's see where we need to be testing. Okay, testing intervals of concavity. Okay, I'm gonna clean this up a bit. Let's see. I got to factor out a 1/3. In fact, a negative 1/3. I'm gonna factor that out. So we get negative 10/9 in the front. That gets rid of the denominator and the negative. This is x to the negative 4/3. I'm gonna write that as 1 over x to the 4/3. Okay, and then this is now a plus 2. And this is going to be x to the 1/3 in the denominator. In fact, I'm even going to take out the x to the 1/3 in the denominator. So negative 10 over 9 times the cube root of x. So if I take out x to the 1/3 from this, it just leaves with an x. So this is 1 over x. And then this is just plus 2, like that. So that's pretty convenient. Okay, there is our second derivative then simplified. Okay, find the values of the C2 values, right? The critical numbers now with respect to the first derivative. So this is where the second derivative is equal to 0 or where the second derivative does not exist. Well, we have that g prime of x does not exist the same place where g prime of x didn't exist, and that's where x is equal to 0, because it's not in the domain of the second derivative. Alright, so the domain of g double prime is that x is not equal to 0. And where does g double prime of x equal to 0? So 0 equals g double prime of x, right, is equal to negative 10 over 9 cube root of x times 1 over x plus 2. We can set each of the factors equal to 0. Well, negative 10 over 9 cube root of x is not equal to 0 for any value of x. But 1 over x plus 2, that's equal to 0 if x is equal to negative 1/2. The values to test around, okay, for concavity are at 0 and negative 1/2. So let's go to a new layer and try that out. Okay, so we have all real numbers, that's the domain of G, and we take out negative 1/2 and we take out 0. Okay, let's see, at negative 1/2, right, we have that the second derivative is equal to 0, right? But at 0, we have that the second derivative itself does not exist, even though the function g does have a point there, right? It is the point with coordinates 0, 0. Okay, the intervals for us to test on are from 0, let's see, 0 to -1/2, an open interval, and then from -1/2 to 0, that open interval, and finally from 0 to infinity. And let's choose test values within each. So like -1, and how about -1/4, and how about +1. Okay, so we can test there. We're going to test in the second derivative. So what is g double prime of -1 going to look like? What is g double prime of -1/4 going to look like? What is g double prime of 1 going to look like? All right, let's take our factored form of g double prime here. G double prime of x is equal to -10/9. Oh, let me put that. -10/9 cube root of x times 1 over x plus 2. Okay, so we have two factors, right? We have this factor, we have this factor. So let's start with that -1, right? G double prime of -1. Okay, so this is, we have -10/9 times the cube root of -1, so we have negative over negative. Okay, we have a negative over negative here, which is ultimately going to be positive. And then we make x negative over here, right? We get 1 over -1 plus 2. All right, let's see, we get -1 plus 2. Okay, so we get negative over negative, which is positive, and we get 2 minus 1, which is also positive, so overall positive. G double prime of -1 is greater than 0, and therefore the function is concave up on the interval 0 to -1/2. And now at -1/4, g double prime of -1/4. Okay, so again we have -10, so we can say the numerator is negative, the denominator is 9 times the cube root of a negative, so a cube root of a negative is negative, so we have negative over negative. This is going to be a positive ratio. 1 over -1/4 is -4, and then add 2, so we're going to get a product of a positive, and -4 plus 2 is negative, so positive times negative, which is negative. So g double prime of -1/4 is less than 0. We have concave down on the interval -1/2 to 0. And testing now at 1. G double prime of 1. We have -10, so we have negative, okay, over 9 times the cube root of a positive. So that's positive in the denominator. And then 1 over 1 is 1, so we have 1 plus 2, and of course that's positive. So we have a negative times a positive, which results in negative. So we have the function is concave down on the interval from 0 to infinity then. So g is going to be concave up on the first interval, which was 0. Oh, I'm sorry. Sorry, that's not 0. What am I writing? -infinity to -1/2. Sorry about that. Okay, right. So g is going to be concave up on that interval. -infinity to -1/2 open. G is concave down on the other two open intervals that we had. -1/2 to 0 and 0 to infinity. Alright, so we have intervals of concavity. What about inflection points? We were doing that in purple earlier, right? Where is there a change in concavity? Okay, these are the only two potential places where we could have that happen, and we did find that that happened in between these two locations right here, right? So as we crossed over from -1/2, okay, at -1/2, that's where we have inflection, an inflection point, because the concavity goes from concave up to concave down, so we have a change in concavity. Okay, And then it's concave down on both sides, okay, of, this is where, right, to both sides of where x is equal to 0, it's concave down, so we have no inflection point. Okay, we have no inflection point at 0. So we have one inflection point. That one inflection point is where the input is negative 1/2. Okay, the inflection point is at the point with coordinates negative 1/2, g of negative 1/2. Okay, so let's find the y value. What is g of negative 1/2? Let's go back to the original function. Okay, so recall, here's our original function, 5x to the 2/3 minus 2x to the 5/3. So 5 negative 1/2 to the 2/3 minus 2 times negative 1/2 to the 5/3. Alright, so let's find out, approximately what that is. I think at this point I'm going to go to the calculator. Right, this is what we're going to do. 5 times the cube root of negative 1/2 squared, right, minus 2 times the cube root of negative 1/2 to the 5th. Right, so 5 times the cube root of 1/4 minus 2 times the cube root of 1 over negative 1 over 2 to the 5th is what? 32. Go to the calculator. G of negative 1/2. So calculator is giving me approximately 3.7797, so approximately 3.78, or approximately 3.8 as the y coordinate. Okay, so that is, we have, the graph has an inflection point at approximately negative 0.5, 3.8. Okay. All right, so we now have intervals of concavity listed. We also have the inflection points. We can do a sketch of the graph. In fact, we were working on a sketch of the graph earlier. Here's what we had, and now we can continue with that. All right, D. A sketch. Okay. Okay, y equals g of x. Again, we have a point 0, 0. Okay, we have, remember that g prime of 0 does not exist, and g double prime of 0 does not exist as well. Okay, but nonetheless we have the point 0, 0. Alright, let's label that 0, 0. Now we have the point at 1, 3 is an important point. So at 1, 3 we have an important point that is a local max. Okay, we had that g prime of 1 was equal to 0, and we found that g double prime of 1 was negative. Yeah, there we go. Less than 0, right, in the interval from 0 to infinity. In fact, right from 0 to infinity, it is all concave down. So from 0 to infinity, the shape of the curve is going to be concave down throughout this region. Notice that this portion right here, we would have increasing and concave down, but on this portion, we would have decreasing but concave down. Okay, we had another important point at negative 1/2. Okay, let's say this is like negative 0.5, and then go up to about 3.8. So if this is 4, okay, if that's 4 right there, then about 3.8, so negative 1/2, 3.8. Okay, that's an important point. Negative 0.5 and approximately 3.8. That is our inflection point. Okay, that's the coordinates for our inflection point. So we have a change in the concavity. Right. Between negative 1/2 and 0, we had the function was concave down. But to the left of -1/2, we had it was concave up. All right? So between these two, right, it's concave down within this interval right here, but it is concave up all the way throughout this part of the domain out here. What about the increasing and decreasing nature of the function? We had that it was decreasing throughout all of this region here. Right? It is decreasing, decreasing, decreasing all the way to 0. And then the function is increasing until we get to the point 1,3, and then it is just decreasing for all time after that. Now we have to put this information together into the shape of the curve. Okay, how do we have a function that is decreasing yet concave up? It must only be a portion of this. Right? Let's see. How about go blue? Decreasing but concave up. Then the shape of the curve is going to be something like maybe like that. It's never going to curve, right? It's not going to curve so that it starts increasing. Okay? So decreasing yet concave up would be this kind of a shape. How do we get decreasing but concave down? That would be, right, so if this was along this piece right here, or that look right there, then this looks like this. That is decreasing but concave down. So this goes like this, and then it hits a point at the inflection point, where then it curves over like this. Okay, so it curves like that, and then it curves over like this. And then we have the function is increasing concave down, just like that, and then decreasing concave down, which is just like that. So then it's going to actually go through, go through an inverted bowl shape. So that's how it looks. All right, let's figure this out then. So let's graph this in red. Right, so we have that concave down between these two. I think I want to start there. Right, concave down to this point right here. Concave down. All right, and then it goes through, an upside down bowl from here to here. So now we can see why the derivative doesn't exist here, because we can see what kind of feature the graph has there. And this is concave down throughout. This answers the question if it is going to approach an asymptote. It can't approach an asymptote because it is entirely concave down all the way out to infinity. Okay? But this explains why. Right, why we had that the derivative did not exist there. Okay, and then beyond that point to the left, that's where we have its concave up, but it is still decreasing. So concave up but decreasing, so something like this. Concave up but decreasing, inflection, concave down but decreasing. We have a local min right here. Okay. Then it is concave down but increasing until it nice and smoothly and continuously goes through a local max at 1,3, and then it continues onward by decreasing concave down all the way out to infinity. Okay, so your assignment online. See, it could take some time to do this. You get some. A polynomial example, find intervals, inflections, local max, local min. Here's one that's part polynomial, part logarithm, right? So you have to be able to take, derivatives, of course, first and second derivatives. Okay. Another polynomial example here, a little graphical analysis. Can you sketch a curve where the first derivative and the second derivative have some given information? And how about this one right here? A whole bunch of pieces of information to put together. When the first derivative is equal to 0, what does that tell us about the curve? When the first derivative is negative on an interval, what does that tell us about the curve? The first derivative is positive on some interval. What about if the second derivative is equal to 0? Right? Where would the second derivative equal to 0? At what potential type of points? What happens there according to the shape of the curve? Right? Okay. The shape of the curve might change where the second derivative is equal to 0. How? We have the second derivative is less than 0 on these intervals, and the second derivative is greater than 0. Okay, and then of course we have the limit at infinity. Back to that again. What does that describe? What type of graphical features are those? Right, that's a review. You can see from these graphs here what feature that could be that it is describing. Okay, graph of the function is shown. At what points are the following true? The first and second derivative are both positive. At which of these points would that be true? First and second derivatives are both negative. Okay, first derivative is negative, second derivative is positive. If you have any questions about any of these, feel free to schedule an office hour. We can discuss it further there. Okay. Another polynomial, find a bunch of things, pick the right graph. Are you able to sketch it by hand? You should be able to sketch by hand a reasonable graph of something like this. Okay, another one, same thing, slightly different looking function. Okay. All right. Another one, a trigonometry one. Okay. Can you take derivatives of trigonometric functions? Can you solve trigonometric equations? Then you apply the technique to this example as well. And this is an interesting one as well. E to the negative x squared is like the Gaussian curve, bell-shaped curve like you see in statistics, for instance. So I also wanted to have you play around with that one a bit. Let me know if you have any questions. Okay. Take care.